Hello everyone, today I will be going over coordinate transformations. These are basically operations that you can do to a certain set of points that will transform them into a different set of points. So the main ways of doing transformations is a translation, dilation, reflection, rotation, and I'll also be going over function transformations in this video. Alright, so first, generally a translation. So this is where you have some original line or set of points, and you will grab it and move it somewhere else and offset it by a certain amount of x and y. So let's say, we want to move it down about 3 units. So this would be y is -3. So b would be -3, a would be 0 here. And every single point from the original function has been transformed into this new set of points. And whenever we do a transformation, we'll call the original points x and y, and we'll call the new transformed points with this prime. So it kind of signifies that they aren't the original. They're a derivative of what the original points were. And we can not just moving up and down, we can also move side to side. So take every point and move it about 2 units to the left, or to the right in this case. So here we're adding 2 to every x value of these coordinates. So it would look like x plus 2 comma y for the new position. But then we can't just only move one direction or only move the other. We can also just move freely in both directions. So here we would be moving about 3 units to the left and 2 units up. So that would be x -3 and y plus 2. Translation is the most basic transformation, because you're not changing the graph at all really, you're just moving it and sliding it across the plane. Now dilation, so the main effect of dilation is the scale factor. So let's say we had a point right here, so 1, 2, and we want to scale it by 2. So the y value will be scaled by 2, so it goes from 2 to 4. And the x value will be scaled by 2, so it goes from 1 to 2. So we'll end up with this. So if this was I prime, or this was I, this will be I prime. And we could even do that to a bunch of points. So let's say we had some square like so, makes this, or I guess this would be a rectangle. And we can simply, every point can be scaled from the origin. So we can just look at the corners. This will go there. We're multiplying both the x and y by 2, because the scale factor would be 2 in this case. And then all of these points would also be scaled up, and so we could actually complete the shape. And so this would be effectively dilating this smaller rectangle by a factor of 2 from the origin. And if you'll notice, the length of these sides are all twice as much. If it was a factor of 3, it would be 3 times as much, which would make the area of this bigger rectangle twice squared as much, or 4 times as much. But we can also dilate not just around the origin, but any point. So let's say instead we were dilating around 3, -1, and we had a shape like this. So we got 1, 1, -1, -1, -1, -1, and 1, -1. And how about this time, let's do a factor of 1.5, so 1.5. So this point is 2 away. 1.5 would be 3 away, so this would be a new corner. Then this one is 4 away, so 1.5 that would be 6 away. This is 2 up and 2 across, so it would end up being 3 up and 3 across. This is 2 up and 4 across, so it would end up being 3 up and 6 across. And so this would be the new shape. And again, we can see all of the lengths are the scale factor amount bigger. And let's say we're given these shapes, but we weren't given the center of dilation. So we didn't know this point. What we can do is if we draw a line through a point and its original, and let's do these two and these. You'll notice they all go through what the center of dilation was. So even if you weren't given the scale factor, but just what the original points and the new points were, you could determine the scale factor by seeing the factor between the side lengths, and you could find the center of dilation by creating a line that goes from an original point to the new point, and seeing where two of those different lines would intersect, because they would always intersect at the center of dilation. You could also, because we know this is 1.5, we know this distance is always going to be 1 minus the scale factor is 0.5. So we know in total it's going to be 1.5. We see, oh, we know this extra part is going to be a third of that. So we're going to need 3 distance in total from here to there. This would be the formula you would use for a scale factor of C and a center of dilation of A comma B. Now reflection. So this is we're going to take some set of points and reflect it over a line. So like you're looking in a pond or a mirror. So first let's do vertical reflection. So we're going to reflect across the x-axis, and that means the x values won't change, but the y values will be flipped and become negative. So every single point here is just the negative value of whatever this was. And if this was the original, and we could even have, if this is the original, we could just flip it and it would go right back to where it was. And then there's also reflecting across the y-axis. So every point, we keep y the same, but we instead multiply x by -1. So this goes there, these swap, this goes there, and this goes there. And so reflection can even intersect with its original function if here we would be at x is equal to about 3.5 and 1.5, and here it's -3.5 and 1.5. So we see there should be an intersection there, because they both pass through 1.5. But the x and y axis aren't the only things we can reflect across. We can reflect across any line. So we could even do a general line. So let's say we wanted to reflect across the line y is equal to 1 instead of the x-axis where y is equal to 0. So it would generally look like this, right? It looks the exact same, and actually it is equivalent to a normal reflection, but then just transformed up. So here, instead of x comma negative y, it would be x comma negative y plus 2c, where c would be whatever the horizontal line is equal to. And we could do a similar thing with a vertical line. So let's say we wanted to reflect it across this line, then generally it would look like this, and this would extend in that direction. But those are just vertical and horizontal lines. What about a straight line that isn't perfectly flat or perfectly up and down? A general line of y equals mx plus b. How can we reflect something about this. Alright, so if we're just doing a random line, first let's find what the equation of this line is. So it looks like we go over 2 up 1, so it's going to have a slope of 1/2. And it looks like its y-intercept is -3/2. And so we have to reflect this set of points around the line 1/2 x minus 3/2. What we can do is reflections are always going to be perpendicular to this line. So we know all of these points need to be, all of the kind of where the points will move will be along this line that is perpendicular to the line of reflection. So let's just choose one of these points. Let's do this one. So it's -3, 2. And so we can write an equation for it. Y is equal to, we know its slope will be perpendicular, which means it will have the negative reciprocal of the same slope. So it'll be -2, and then we can use point slope form, so it would be x plus 3, and then plus 2. And if we want to simplify it, we could get, and then we can set, because we want to find where this would intersect with a line. Because we know however far it travels to get to the line, it will travel exactly that much further to end up reflected across from it. So we can set these equal to each other to find the point of reflection. So I will do that real quickly. And we just plug that back in. So -1. So we know it will reflect at -1, -2. So this will be where it goes through. And we know however much it took to get there, it's going to go exactly that distance again. So we see it moved 2 in the x direction, so we'll move 2 in the x direction again. And it moved 4 in the y direction, so we'll move 4 in the y direction again. So we'll end up right here. And we could do that with the rest of the points, and we would get a line something like that. So the strategy for reflecting any point across a line of reflection, given the equation for the line of reflection, simply draw a line including that point that has a perpendicular slope to the line of reflection, and then find that intersection point, and then simply go twice as far as the distance here. So the change in y will be doubled, the change in x will be doubled, plus this original point. So it would be x, y is equal to this original x point plus 2 times the distance traveled. So a, or a comma b will be the value of intersection, so a minus x. And y is just y plus 2b minus x. And actually something cool about reflection is if you know this is kind of the point of reflection, you're essentially just doing a dilation of -1. So instead of moving one this way, we'll move one in the opposite direction. And now let's go over rotation. So rotation will, if you have any point, it will rotate it around, keeping the same magnitude but changing the angle. But you can move either clockwise or counterclockwise. So let's take this point and let's start going through what some of the most common rotations would look like. So 90-degree clockwise, which is the same thing as 270 degrees counterclockwise. So 90 degrees is going to be end up like this, 270 ends up like this, so we go to the same spot. If you look, it's going to flip x and y and make the new y value negative. So this is 3, 1. So first we'll flip them and we get 1, 3, and then we're going to make it 1, negative 3. So 1, negative 3. And we see we rotated it over here. And let's do another rotation. So another 90 degrees clockwise will get us to 180 degrees clockwise. And minus this will get us to 180 degrees counterclockwise. So it's the same amount because you're going halfway in either direction. So this will just simply make of the original point it negative x, negative y. But we can also follow this. If we apply this again to this new point, 1, negative 3, we'll flip them. We get negative 3, 1, and then make the second one negative, negative 3, negative 1, which is what we would also get here. So negative 3, negative 1, and then here, another 90 degrees, we would end up here. Following the same rules. And any one of these individually, you can see this formula for what you would get, but just following it, you can apply the rule multiple times. And if we do it another time, we would just get back to right where we were. So these, we're kind of moving. Each point will be in a new quadrant. So remember, this is quadrant 1, 2, 3, and 4. So if we're moving counterclockwise, we'll actually move along with the quadrants. We'll go from 1 to 2 to 3 to 4 to back to 1. But if we're moving clockwise, we'll go 1 to 4 to 3 to 2, then back to 1. But then, what if we're not doing an even number or a kind of a nice number rotation? What if it's kind of just a random value? So let's say we're doing 15 degrees or something. Then we'll have to use this formula. So r will be the magnitude, so it will be the square root of x squared plus y squared. And then a tan 2 essentially just tells us the angle. So if we're looking at this, this would have a magnitude of a little bit over 3, and then this would be the angle. And so if we're doing another angle of 15 degrees, we simply just add a little bit more here, and we'd end up somewhere about there. And so all we're doing is just adding this new theta to the original angle for both x and y. And we're making sure it will have a magnitude of r, which is x squared plus y squared away. And something cool is that for dilations, reflections, and rotations, the way you can do the same thing is a dilation of -1 is the same thing as a reflection over the origin, which is the same thing as a rotation of 180 degrees around the origin. And if you choose a new point for all three, it will be the same. So there are ways to do each of these operations in different ways, but using them all together, you can do a whole lot more. So finally, function transformations. So we've gone over ways to kind of see what a set of points would look like, and then apply some transformation to that set of points, and get a new set of points. But we can also do it directly to a function before even seeing the original points. So if we have some original function, y is equal to f of x, so y is some function of x, but then we want some transformation of that, so we can on the outside, we can multiply by numbers and add numbers. And on the inside, we could change it to multiply and add inside, or multiply and subtract, or divide and subtract, or whatever we want to do. But generally, if we're looking at outside, so we'll change the y. So whatever we multiplied by, we'll multiply what the original y was, and whatever we add, we'll add. And then inside, whatever we add will be subtracted, and whatever we multiply will be divided. Generally, this is a little bit tricky, but for outside of the function, you will just follow normal order of operations. So we see this is a times the function, we'll get ay plus b. But inside, we essentially do inverse order of operations. So where we look at this, we would normally want to multiply first and add second, but instead we look, if we want to kind of get x by itself, we would first subtract d and then divide by c. So you're essentially, if we have a cx plus d inside the function, we're going to set it equal to some random variable, and then, so we'll subtract d, and then divide by c, and we're down to getting x is equal to x prime minus d over c. So whatever the original value for any of the points in the functions was, we can subtract d and divide by c, and we'll get some new value. So let's say there was some line like this. If we multiply by some value on the outside, it will just multiply all of the y values by a certain amount. If we instead added b, it would just simply shift everything up a little bit. If we have some multiplier on the inside, it's going to shrink all the x's down, like so. And then we can also shift it around in the x direction, so we could end up like here. The main ways of what these expressions can do to a function are vertical and horizontal, translations, stretches, compressions, and reflections. So vertical will always be y stuff. So anything you apply to outside the function will be vertical. So multiplying or adding will simply move, the x values will stay the same, the y values will move up or down. And reflection will simply be negative that. Horizontal is whatever is inside. If you have some function that's changing inside here, that will change it horizontally, so you don't need to change the y. The x's will shrink and compress, and multiplication will, for x, will compress it, but for y will stretch it, and reflections would be the same, but negative inside of the function. But yeah, simply for y, follow order of operations, and for x, simply solve for whatever this would be on the other side. And there's also other ways of doing function transformations. So if we had y is equal to the absolute value of f of x, let's say this was the original function, the new function would be the same, except we would just have that little hump, and this part would go up. So essentially, it's just this negative f of x part, except it doesn't apply for when x is already positive. And we could even do this, which would, anything that's over here would reflect up there. And it's going to look weird because absolute value will just completely reflect everything over, regardless of its direction. And then something else that you can do is with logarithms. So let's say you had some exponential function. If you do log of f of x, then it will essentially turn this into a log plot. So if this is some exponential function, it will turn it linear. If this was some quadratic function, it's going to turn it into a log plot. several other functions, or probably an infinite number of other functions you could apply and do some kind of function transformation. But normally it will simply be linear transformations to a function, which will result in vertical and horizontal translations, stretches, compressions, and reflections. And that is everything you need to know about basic coordinate and function transformations. Let me know if you have any questions, and thank you for watching.